Previously, we have discussed about some of the methods in which we can solve a system of linear equations, and specifically, we've seen the matrix inversion method, Cramer's rule, Gaussian elimination, and also the Gauss-Jordan method. Today, I'm going to give you an introduction to MATLAB and see how we can use MATLAB as a programming tool to solve equations. And also we will see how to enter the data representing the equations into MATLAB and store them as variables. And we will see the different steps involved in the calculations, right? Like we computed the determinant of a matrix, the transpose, the inverse of a matrix, and we applied Gaussian elimination, Gauss-Jordan, and we obtained the row echelon matrix or the reduced row echelon matrix. And then we also saw how we can determine from observing the row echelon matrix whether the system of equations has a unique solution or multiple solutions or no solution, right? So we will see how we can use MATLAB to observe all these things, and also to see how we can solve the system of equations using MATLAB. Okay, so the first thing is I want to get you started with some basics of MATLAB. So basics of MATLAB. Now, if you notice here, what I've typed here, it starts with a percentage sign. So whenever we start a line with a percentage in front, it's a comment. So percentage sign means it's a comment. That means it's not a part of the program. Okay, it's just a comment for our reference. So when we want to have some information for our own reference, we can put such things as comments, but this is not a programming instruction to the computer. Okay, so a comment line will not do anything. It is just for us so that we remember what we are doing or to highlight what we are doing. Okay, as in this case, I'm just wanting to highlight that we are going to study some basics of MATLAB today. The next thing we want to do is we want to assign values to variables. Okay, the most basic thing is, for example, if I define a variable called t and assign it a number 1. Okay, so t equal to 1, that means the value 1 gets stored in that variable t. So every time I use t, it will give me the value 1. Or suppose I want to use this t in my calculations. If I say t plus 1, so t is already 1, so the answer should be 1 plus 1 equals 2, right? So the answer is 2. Or I can say, let's say, w equals t multiplied with 3. So by the way, multiplication, the operator is star. So if you put the star operator, that's multiplication. So t times 3, so since t is assigned as 1, so 1 times 3 is 3. Okay, so like this we can use assign values to variables and then use those variables in our calculations. Now whenever we type a command like this, we can put a semicolon in the end. The semicolon basically suppresses the answer to be printed on the screen. So previously, when we didn't put a semicolon, the answer got printed on the screen. And if you see here, we said w equals t into 3. That means the answer is getting stored in a new variable called w. So the answer is in w now. So w equals t into 3, it is stored in w. Now if I put a semicolon in the end, it will calculate the value and keep it in w, but it will not show it on the screen. So when you put a semicolon in the end, so it's in w, but it won't show it in the end. So let's say we create another variable, v equals w into 5, for example, and we put a semicolon in the end. So now what will happen is the value of w, which is now 3, will get multiplied by 5. So 3 into 5, 15, and that will get stored in the variable with the name v. So but because we have put a semicolon, it will not print the answer on the screen, but it is there in the memory of the computer. So whenever we type v, if you want to print it out, we just need to type v without any semicolon. So you see v equals to 15, or we can use that v in subsequent calculations. For example, I can say m is equal to uh, v plus 5. So obviously that answer for m should be equal to 20, and I'm going to put a semicolon so that we don't see the answer on the screen, but in the memory m will have a value of 20, and if I just put m and you see it is v plus 5. Since v is equal to 15, m is now 15 plus 5. So this is how we assign values to variables, and then use those variables in our subsequent calculations if we need to. Now, one important thing regarding variables is, I'm going to write a comment here, variable names, the names that we give to the variable, like we gave here t, uh, v, w, m, right? It can be any letter or any word also. Variable name is case sensitive. What do we mean by that? If we say the variable name is case sensitive, it means small m is not the same as capital M, right? So M and capital M are not the same. They are two different things, okay? Similarly, T and, let me write that as a comment, small t and capital T are not the same, right? So if I put T, we assign the value as 1, but if I put capital T, it says undefined function or variable. So we did not define capital T, right? Similarly, if I write small m, it has a value of 20 because we have defined it and assigned a value to it. But now if I say capital M, it's not defined because we did not use capital M in our uh, commands up to now. Okay, we know nowhere did we use capital M here, right? So that you have to be careful when you're writing code in MATLAB, that your variable name is case sensitive. For example, I can have a variable name, say the theta equals t. So whatever theta equals, let's say m. Okay, since the value of small m is 20, that 20 will get assigned to theta now. So I can have it. Have stored the value of m in another variable called theta. I just made a copy of it. That is right. So theta equals 20 now. Now, if I write it as theta, it will give me undefined function, right? It has to be exactly the same way we defined. So if you have used all small letters, then it has to be exactly in the same way. Okay, if you have used this as our variable, then you have to write exactly with the first letter as capital. So the variable names are case sensitive, so they have to be used exactly as they have been defined. Okay, so far you have seen how we can assign numbers to variables. Now we will see how do we define vectors. So the first kind of vector that we are going to see is a row vector. How do we assign or enter a row vector in MATLAB? So again, let's give it some name. Okay, I'm going to use say small m now, and by the way, if you redefine a variable with a new value, it will get changed. For example, small m now has the value of 20. Now if I write small m equals 15, what will happen is that 20 will get deleted from m and the 15 will be assigned to m. So the 20 is no longer there. So if we type m again, it will now show as 15 only. The previous 20 is now deleted. Okay, so once a variable has been assigned a new value, its old value will disappear. So let's go back to the row vector. So if you want to define a row vector, so I'm going to call it as a capital M. You can give it any name as long as it follows certain rules. Okay, so I'm going to call it capital M equals. So to define a row vector, we'll just enter the numbers as with a space or a comma between them. So let's say I have a row vector 1, 2, 3, right? So that's a row vector with 3 numbers. So it's a row vector 1, 2, 3. Or I can have, if I want 4 more numbers, say 4, 5, 3, 5, -2, and so on. So that's a row vector where the elements are assigned in a horizontal way, and we can either put a space between the numbers, or we can also put a comma between the numbers. Either way, it will treat M as a row vector. Now, if you want it as a column vector, then all we have to do is, instead of a space or a comma, we'll have to use a semicolon. Okay, so we put a semicolon here. Okay, the space is optional. That is only for us to see the numbers clearly on the screen. So we can have the space after the semicolon or not, doesn't matter. So just to illustrate, I'm going to remove that. And you see now that 1, 2, 3 has come as a column vector. It's a vertical column now, right? So if we put the semicolon between the numbers, it moves to the next row. Okay, the semicolon will shift the number to the next row, and a space or a comma will put the next number in the next column. Okay, and so suppose we want to have two different names. Okay, so let me say I'll call the row vector as m1. So that's a row vector m1, and then I can have another number, another vector, which I'll call as m2, and make it as a column vector. And for column vector, we have to put a semicolon between the numbers. So now we have a semicolon. So now m2 will be a column vector. Okay, so now we can say m1 multiplied with m2. Okay, if we do this, it will multiply the two vectors, and we are able to multiply this because the number of columns in m1 and the number of rows in m2 are same. If they were not same, then we wouldn't be able to multiply the two vectors. For example, if I multiply, say, m1 with another vector, m1 is a row vector, but I'll create another column vector, say 1, 2, 3. So if you notice, m1 has how many numbers? 1, 2, 3, 4, 5, 6, 7, 8 numbers. So it has 8 columns in m1 and 1 row, and I'm multiplying that with a column vector which has only 3 rows. And you see now it will say there is an error in the multiplication because the dimensions must agree. That means the number of columns and the number of rows should match. So if we have 8 columns, column 1, 2, 3, 4, 5, 6, 7, 8, that matches with the 8 rows, 1, 2, 3, 4, 5, 6, 7, 8. So only when they are matching it could multiply. When it is not matching, it says you can't multiply because matrix dimensions do not agree. So when you are performing multiplication operations on matrices or vectors, you must ensure that the matrix dimensions agree. Okay, so now we have seen how to enter a row vector and a column vector. Now let's see how to enter a matrix itself. So okay, how do we enter a matrix in MATLAB? To enter a matrix in MATLAB, let's call that matrix, say, M. I'll call it again, say, capital M equals. Now we want to enter, say, 1, 2, 3. That's our first row. So we put a space or a comma here. So that will be a row, and then we want to go to the second row. To go to the second row, we put a semicolon, so that will take us down to the second row, and let's say we want to put some other number, say -1, 3, 4. okay, and I've used spaces. Okay, you can also use commas in between. Again, we put a semicolon so that it goes to the next row, and then we can say 6 4 7, for example. Okay, I'm just randomly putting some numbers. So we now have entered a matrix M, and because I'm not going to put a semicolon in the end, so if I put a semicolon, it will store this matrix in the variable M, but it will not print it out on the screen. But we want to see it on the screen, so we will remove the semicolon and hit enter. And you see we have this matrix which has 1, 2, 3 in the first row, -1, 3, and 4 in the second row, and 6, 4, 7 in the third row. And like this we can create matrices of any dimensions. Okay, we can have any number of rows and any number of columns, and we just need to enter them correctly. Okay, so that's how we enter a matrix. And again, I'm going to retype that same command again. To see your previous commands, you can use the arrow keys on your keyboard. So it will show you the command history, the previous commands that you have typed. And from that, you can select any of the previous command if you need to. So I'm going to select this command, and I'll put a semicolon now. Now, if you put a semicolon, as I said before, it will not print the output on the screen. So M is now in memory, but it is not printed on the screen. And when we just type M, it will show it to us what is the value. Okay, so that's the way we enter a matrix. Now, the way why we are entering doing all of this is, if you remember, we had our equations as ax equal to b, right? Ax equals b. We had our matrix equation in this form, where A is the coefficient matrix. A is the coefficient matrix. By the way, let me make one correction here. The x, we have used a capital X, right? Okay, Ax equal to b. A is the coefficient matrix, and x, okay, x is the vector of variables like x, small y, and small z. Okay, so x is the vector of variables, and b would be a vector of the numbers which are on the right hand side of the equation. So b is the vector of numbers on the right hand side of our equations. Okay, so now we want to enter the A matrix, we want to enter the B vector, and then find the solution for the vector x, which is the containing the variables small x, small y, and small z. Okay, so I'm going to enter one of the matrices that we have. I've already entered it, so I'm just going to bring it up now. So I have a matrix called A, capital A, which is representing our first example that we did, which gave us a unique solution. Okay, so the coefficient matrix for the first example that we did was this particular A that I have brought up on the screen here. I have already entered it before I started the lecture, and I had it in my variables here. If you see the variables, I have it here. Okay, now the equations we had was the corresponding B vector representing the right hand side of the equations was this 505, and if we put these together we'll get the augmented matrix. So augmented matrix. So to get the augmented matrix, we just need to join these two matrices, right? So we have A, and we want to join the B to the right side of A. So we just put a space or a comma and put the B there. So now if you print it out, so that's our augmented matrix that we had earlier, and we use this to solve our equations. So basically the equation is x minus y plus 3z equals 5, 4x plus 2y minus z equals 0, and the last equation is x plus 3y plus z equals 5. And we solved it using different methods. Okay, now let's do a few basic MATLAB commands here. The first thing we need to check is whether the system of equations has a solution or not, and we did that by computing the determinant, right? Determinant. So if determinant equals 0, then the coefficient matrix A is singular, and in that case, if A is singular, that means no unique solution. Right, we have said this. So let's see now how can we use MATLAB to compute the determinant of a matrix. So the command in MATLAB to compute the determinant is det. So we just need to type det, and then in rounded brackets, inside rounded brackets, you have to enter the variable name of the matrix. So our matrix, the coefficient matrix is A, and it is stored in the variable capital A. So we have to put capital A. So that means we are telling MATLAB to compute the determinant of the matrix stored in the variable capital A. So when you do that, you get 40, and that is exactly what the value that we computed when we solved these particular equations in our earlier lectures. All right, so the MATLAB command for computing the determinant is det, and if you put any other number there, for example, we had a previous matrix here as m, right? So we can compute the determinant of that m and see whether it is singular or not. Okay, so the determinant of m happens to be 1. Okay, so since both these matrices have a determinant value that is not equal to 0, therefore they are not singular. So the A matrix that we have used for our equations here, that represented a system with unique solution, and therefore the determinant is non-zero, and therefore the matrix is not singular. If it is singular, then we cannot solve it. All right, so the MATLAB command to find the determinant is det. The next MATLAB command I want you to know is the transpose of a matrix or a vector. Transpose of a vector or matrix. Okay, so how to take the transpose of a vector or a matrix? So let's say we have, I'll start with a vector. Let's say I have this vector m1. Okay, m1 is in the form of a row now. Okay, it's a row vector. I want to make it as a column. So we simply write transpose of, the command is transpose m1, the name of the variable. So m1 is a row vector. After transposing, it has become a column vector. So let me type m1 directly. So m1 is a row vector. The transpose of m1 is a column vector, right? And whenever we write such commands, we can store the output in a different variable. So I'll call it as m1 underscore trans equals transpose m1. Okay, so I'm storing the transpose of m1 in another variable whose name I'm defining as m1 underscore trans. So you can use any name. So it is now stored in that variable. So every time I type m1 underscore trans, it will give me that answer. Okay, so it is now stored in memory with that variable name called m1 trans. Similarly, if we have our A matrix, right? So I want to find the transpose of the A matrix. So uh, all we have to do is we need to, okay, in place of M1 I will put A. So transpose of A will convert the rows into columns and columns into rows. That is what a transpose is. So 1 minus 1 3, that's the first row that became the first column here. 1 minus 1 3, 4 2 2 minus 1, so that becomes the second column here. 4 2 minus 1, the third row becomes the third column. So the rows and columns have been interchanged. Okay, so that's the command for transpose. But there is also another command for transpose which is a bit shorter. Rather than writing transpose of A, we can just write A single quote. Okay, that will also create the transpose of A. So if we just write A transpose, you see it gives the same answer. Transpose A and A single quote, it gives the same answer. Similarly, M1 underscore trans, right? So that's the value we had for M1 trans, which is the transpose of M1. So rather than typing it as transpose of M1, we can simply write M1 single quote, right? So that would still give us the same answer. Okay, M1 single quote. So it's for transpose, you can either use the transpose command here, as in here, or you can just write the variable name representing the vector or matrix and put a single quote next to it. So that would create the transpose of that corresponding vector or matrix. Okay, so we have seen how to compute the determinant and how to compute the transpose of a vector or a matrix. Next, we will see how to compute the inverse of a matrix. So we have the matrix A, which we used for solving in our previous lectures, and we want to find the inverse matrix of this A, and we will store it in a variable. I'll call the variable A underscore inv. Okay, and that's the variable which will have the inverse of A, and the command for uh, computing the inverse in MATLAB is inv. So you simply type inv and inside round brackets put the variable that contains your matrix. So our matrix is stored in the variable capital A. So we are simply going to type uh, inverse of A. So now when we hit enter, so that gives us a matrix that is nothing but the inverse of our original coefficient matrix. And what is the property of the inverse matrix? If you multiply the inverse of a matrix with with the matrix itself, that should give us the identity matrix. So you see here, the identity matrix, it contains 1 on the diagonal and 0 everywhere else. So uh, the product of a matrix with its inverse gives us the identity matrix, which is uh, having ones on the diagonal. So the diagonal elements are 1 and the off diagonal elements are all 0. Okay, and it's because of the computation it shows it with the decimal point, with the numbers after the decimal point as well. Okay, and that's to check whether this matrix is indeed the inverse of the original matrix. And to compute the inverse matrix, all you did was type the inv command in MATLAB and it gave you the answer. Now, if you remember, when we computed the inverse of a matrix, we've done it using two different ways. One was in the matrix inversion method, where we found the cofactor matrix, then the adjoint matrix, and from the adjoint matrix, we computed the inverse matrix. And another method which we used more recently to compute the inverse matrix was using the Gauss-Jordan row transformations, right? So when we applied the same row transformations of Gauss-Jordan to uh, the identity matrix, we ended up with an inverse matrix, right? So MATLAB uses its own algorithms to, but similar to the way we have done, okay, but more optimized algorithms to compute the inverse of the matrix. So we have seen a determinant inverse, and transpose, right? The three commands. So let me summarize that. For determinant, the MATLAB command is det, and inside the bracket you will put the variable name. Okay, and for transpose, the command is transpose of A, or you can simply write A single quote, right? So A transpose. So either way you'll get the same answer. And for inverse, the MATLAB command is inv of A. And you can use the assignment operators to store your answers in a different variable. Okay, so we have seen these three commands to find uh, the answer, the inverse, determinant, and transpose of our matrices. Now we computed using the matrix inversion method as the, what do you call it, the solution x equal to a a inverse. I can't write the superscript here on my screen, so it's not a minus 1, it's a, I'll write it as inverse of a multiplied with b. A inverse b gave us the solution for x, right? So let's see if we get the same answer with our calculations, with our MATLAB implementation now. So we have computed a, the inverse of a, and stored it in the variable a underscore inverse. We already have entered the b vector in our system. So the b vector is C is 505. We already have it. So let's try to find the x values. X equal to a inverse multiplied with b. A inverse b should give us the solution to our equations, and that, let's put enter, and you see we get x equal to 0, 1, 2. So the vector x, which contained small x, small y, small z, is if you see from the previous lectures, we solved it and got the answers as x equal to 0, y equal to 1, and z equal to 2. And that is exactly what we have computed using MATLAB as well. So we have multiplied the inverse of the matrix with the vector b, which is the vector of numbers on the right hand side of our equations, and we got the solution, a small x equal to 0, small y equal to 1, and small z equal to 2. Okay, so matrix inversion, therefore we say the MATLAB implementation, you can verify that it's working. Of course, we don't need to verify it, but just for the learning process, we are illustrating this, and you should know how these commands work in MATLAB. And basically what you're studying in this course is to get an understanding of what is happening behind this command. Okay, when you type this command, what are the calculations taking place inside the computer, right? You have got a glimpse of that in the previous lectures. Now today we will just use MATLAB to solve the problem for us, and see the solutions, and we've seen one of them already here. Okay, so we've done one example for the first set of equations that we used for the case which had a unique solution, and it's exactly the same answer that we computed by hand in our lecture. Okay, now let's move on to another thing is the identity matrix, right? So sometimes you may need to generate an identity matrix of a particular size, and the MATLAB command for that uh, is EYE, identity matrix. So if I say EYE, it's I matrix, and we need to specify the dimension of the I matrix. So let's say we say dimension is 3. So EYE3 means it will give a 3 by 3 identity matrix. You see here, It has ones on the diagonal, and the off diagonal numbers are 0, and it's a 3 by 3 matrix, 3 rows, 3 columns. If you write, say, EYE5, so then it gives us a 5 by 5 identity matrix. We can have a 10 by 10 identity matrix. Okay, again, as of now you don't have any need for this, but sometimes we may need to have generate the identity matrix, and the MATLAB command to do so is the command EYE. Okay, so and we can specify the size of the identity matrix that we need. So whatever is the number we put inside the bracket, the identity matrix will be a square matrix of that size. Okay, uh, and we've also illustrated that multiplying a matrix with its inverse gives us the identity matrix, right? So we did that. A inverse multiplied with A. So it is giving us an identity matrix which has 1 on the diagonal and 0 everywhere else. So we have seen that as well. Now let us see some more examples, and we will move into the Gaussian elimination part now. Okay, Gaussian elimination. And in Gaussian elimination, we converted our augmented matrix into a row echelon form. And the row echelon form was nothing but it had you have all the elements below the diagonal as zeros and all the elements above as non-zeros. That's the row echelon form. So you'll see how we can obtain the row echelon form of a matrix in MATLAB. So again, we've done a lot of steps to do the calculations, but MATLAB has a built-in command for it. So you just type the command and it gives you the answer. So let's take our first example, where we had the matrix A and B, the augmented matrix AB. So that's our set of equations, okay, the augmented matrix. So the first 3 rows are representing the coefficient matrix, and that's the B vector, right? Now we want to solve this, apply Gaussian elimination to this, and the way to do that is it uses a command called LU. Okay, it is called LU, stands for lower upper. It converts the matrix into 2 other matrices. One is a lower triangular and the other is an upper triangular, and we are interested in the upper triangular matrix. And our matrix is capital A space small b, right, in square brackets. So we are joining the coefficient matrix and the B vector together, and we use this LU command in MATLAB, and the output, it gives us 2 outputs. One is the lower triangular output, which we'll call L, and the upper triangular output, which we'll call as U. And we will assign the outputs to these variables, capital L and capital U. Now we are not interested in the L part, we are interested only in the upper triangular matrix. So I'm going to suppress this here, and so the L and U are stored, but I want to print out only the U part. Okay, so if you look at the U matrix, which is what is the result of the Gaussian elimination process. So when you see towards the end of the Gaussian elimination process, you will have this these elements below the diagonal of the coefficient matrix converted as 0. Okay, so we have these elements converted to 0, and all the elements above the diagonal, so that's our diagonal elements of the coefficient matrix, all numbers above the diagonal are non-zero, and we have these elements which are below the diagonal, all of them converted to 0. So that is nothing but what we have here is the row echelon form, right? Row echelon form of the matrix. Okay, so we started with the A matrix, the augmented matrix, and now we have the row echelon form, And from the row echelon form, you can perform back substitution. And when you perform back substitution, you will get 4z equal to 8. So that means z equal to 2, which is exactly what we saw here, z equal to 2. And then substitute that z equal to 2 in the second line, in the second row. So that will be 2.5 y plus 1.25 z equals 5. And substitute the z equal to 2 here, you will get the value of y, and then substitute the y and z in this equation. That should give you the value of x. And clearly you see that when you back substitute and find the answers, so I'll leave it to you to verify it, you will get the same answer as in here. So that's the Gaussian elimination part. Now you might notice that there is some difference between this row echelon matrix that we see on our screen here and the one that we computed during our lecture. One of the things that has happened is in MATLAB, it uses certain other operations to make the computation faster and more efficient. Okay, so if you notice this 4 2 minus 1, that was actually the second row in our matrix, right? So the row has been interchanged. So this has been moved as the first row, and the first row has been brought to the second row, and so on, right? So interchanging the rows of our original matrix does not alter the results, but sometimes doing so can make our calculations simpler. And MATLAB would do that to make the calculations faster. But nonetheless, you should still get the same answers. Now, the other thing that you notice here is uh, after the Gaussian elimination process, when you look at the row echelon matrix, which is this one, the row echelon matrix does not have any row which is all zeros. So if you look at the number of all zero rows in the coefficient matrix, that is the matrix in this part, right, to the left here, so you see there is no row which has all zeros. So that means the rank of this matrix is 3. It has 3 rows which are non-zero matrix, non-zero rows. So the rank is 3, and we have 3 variables. So we are able to solve it and get the answer. If we end up with getting an entire row which is zeros, then that would indicate that the system is having no unique solution, or it has multiple solutions, and that could also be seen by computing the determinant of that matrix. Okay, so we see the row echelon form of the matrix, from which we can determine whether there is a solution or not. And if we have it in this form, where the rank is at least the number of variables, we can solve it and get the solution. Okay, now let's take another example. Let me do it. Let me apply the Gauss-Jordan method for the same matrix. Okay, so Gauss-Jordan method. Okay, in Gauss-Jordan method, what we did was we made the diagonal elements as 1, and we made the off diagonal elements as 0. So even the upper half, we made them as 0. So we ended up with an identity matrix for the A matrix, and then finally we had the solutions which we can determine without back substitution. And in that matrix is called as the reduced row echelon form, right? Rather than row echelon, it is called as the reduced row echelon form. Okay, and the reduced row echelon form is what we get at the end of the Gauss-Jordan process, and the MATLAB command to get the reduced row echelon form is just the abbreviation, just the acronyms for this: RREF. Okay, in small letters, RREF. And the matrix to which we want to convert to the reduced row echelon form, which is nothing but the coefficient matrix joined by the b vector, and we put that because that's a matrix that's in square brackets, and that's the command. So the variables that go inside the command or function will be in rounded brackets. So when we hit enter now, you see uh, the A matrix has got converted to the identity matrix. So you see the the first three columns here, that is an identity matrix, and you get the solution directly here. X equal to 0, y equal to 1, z equal to 2, right? So that's our the reduced row echelon form of our original augmented matrix that gives us the solution directly. Okay, and MATLAB did some steps, some row operations to achieve this answer. And if the same steps were applied to the identity matrix, then we would get uh, the inverse matrix. So to check that, I'm going to join the identity matrix with our augmented matrix and then solve it. So RREF, I'm going to join the A matrix with the B vector. Okay, and to that I'm also going to join an identity matrix which is of size 3 by 3, because we have the A matrix which is size 3 by 3, and the command for the identity matrix is EYE, and the size we want is 3 by 3, and we close the square brackets. So now what we are going to have here, or rather let me show you what this matrix is going to look like before I type the command. So basically we have the augmented matrix still here, right? And we have joined the identity matrix to the right of it. So now we will apply the reduced row echelon form RREF command to this. So that means we will get the solution, as well as on the right side we will get the inverse of the original A matrix. So this A matrix will get converted to I, and the I will get converted to A inverse. Okay, and we will finally verify with the inverse of A. So let's check that. So you see now, that's x equal to 0, y equal to 1, and z equal to 2. And that's our inverse matrix of A. So if we recall, we had A, I, and V, right? So when you type A inverse, what is the answer we got? 0 0.25, 125, 0 0.25 minus 0. Exactly the same numbers are there. So that's our identity matrix, sorry, the inverse matrix of A. But this time it has been computed using the Gauss-Jordan row transformations, where the A matrix has got transformed to the identity matrix, and the identity matrix has got transformed to the inverse matrix, right? So INV of A. So that's exactly what we have here on the right hand side, right? So we have the RREF command, by which we can perform the operations of the Gauss-Jordan process to get our solutions. Okay, so we have seen how we can use the LU command for Gaussian elimination, and again the LU command gives us two answers, the lower triangular and upper triangular, but we are interested in the upper triangular matrix. That means the upper triangle is non-zero, the lower triangle, the lower half below the diagonal, is all zeros. Okay, and we've seen it for one of the examples. Now I'm going to do it for a second example, which has multiple solutions. So that's another example that we solved in class previously, and I've stored that matrix in variables A2. I've already entered it in my system and I have stored it. So A2, B2 is the number, rather than A and B, I have stored it as A2 and B2. So that's our system of equations, which is a homogeneous, representing a homogeneous equation, because the right hand side numbers are all 0. So that means it has a trivial solution at the origin. But this particular example is for multiple solutions. So this particular set of equations has multiple solutions. Okay, multiple solutions. So that's our equations that have multiple solutions. And let's check first of all the determinant of A2. Determinant of A2 and see what we get. See clearly the determinant is 0. So if the determinant is 0, we understand that it does not have a unique solution. It either has multiple solutions or it has no solutions at all. So let's do the LU decomposition and see what we get for this. So instead of A and B, I'll use A2, B2 and get the LU decomposition of this, and we are interested in the U part. So let's observe the U part now. So when you apply Gaussian elimination to this system of equations, what you notice is you have an entire row of zeros. So that's an indication that this system of equations has multiple possible solutions. Okay, the determinant tells you that it does not have a unique solution, but it does not tell you whether it has no solution or multiple solutions. To check for that, we perform Gaussian elimination and look at this uh, row echelon matrix. And from the row echelon, we see that because it has an entire row which is zeros in the reduced echelon form of the augmented matrix, so that means this matrix, this system of equations has multiple solutions. And again, that means the number of non-zero rows here in the reduced coefficient matrix uh, gives us the rank of the matrix, right? So if I just, the MATLAB command for rank is rank of A2, right? So if you see now, the rank of A2 is 2, but we have three variables, x, y, and z. So we need at least the rank to be at least the number of variables in order to be able to solve it. Uh, Previously we did for A. So we had three variables and the rank is 3. So it's we are able to solve and get a unique solution. But in this case of A2, the rank is 2, which is less than 3, the number of variables, so we are not able to solve it. And when we see an entire row containing zeros, that's an indicator that this system of equations has multiple possible solutions. Okay, so let me type that. So the U, it has an entire row of zeros, so it represents the case of multiple solutions. And one of the solution, because it's a homogeneous system, we know for sure one of the solution is the origin x equal to 0, y equal to 0, and z equal to 0. Okay, now let's look at a case where the third case where we had a system with no solutions. Okay, and I've already entered the data and I've stored it in the variables a3 and b3. So a3 space b3. So I'm joining the coefficient matrix and the vector of numbers on the right hand side of the equations. So that is another example that we solved in our previous lectures. So this represents a system of equations that uh, that has no solution. And again, when we compute the determinant of the coefficient matrix for this system, you will see that it is 0. Okay, and 10 power minus 16, right? It's almost 0. It's very close to 0. But the MATLAB, the computation, shows some small residual number at the end of the calculation, but it's 6.66 into 10 power minus 16. That is like 0.000000015 zeros and then a 6, right? So that's a very, very small number, which is almost 0. Okay, so that comes from the round off errors in a computational machine. Okay, so that is effectively 0. And now let's do the LU decomposition for this matrix, for this particular augmented matrix, and see what we get. A3, B3, and we are interested in the upper triangular matrix. And now you see uh, the reduced echelon matrix shows that uh, 0x plus 0y plus 0z equals -2. That's the impossible situation, right? How can you add three zeros and get -2? It's not possible, right? So while the determinant tells us that the determinant is 0 and therefore there is either no solution or multiple solution, but when we see a row in the reduced echelon form which has an impossible situation, or which depicts an impossible situation, then we know clearly that there is no solution. Compare this with the previous case where we had all zeros. Okay, this is not an impossible situation. 0 plus 0 plus 0 equals 0. That's quite possible. But that makes the rank less than the number of variables, therefore we cannot solve it. But here, again, the rank is less than the number of variables because the number of non-zero rows in the uh, reduced coefficient matrix is still 2. But we see a situation here which is an impossible situation of adding three zeros and getting -2. That's not possible, right? So rank of A3, if you see, again we get it as 2. Okay, now that gives us an indication that this is a case of no solutions. Now the other thing we want to do is let's apply Gauss-Jordan to both these cases, RREF to our A2, B2, right? So A2, B2, and see what we get. And then we'll do it. This is the case for multiple solutions, okay? This is the case for multiple solutions, and see what happens if we try to do the Gauss-Jordan process. Now clearly you see, first of all, it has not made this number as 0. In the Gauss-Jordan process, we should have an identity here. It should be 1, 1, and 1 here, but it's not able to get that. And all these numbers which are off the diagonal should be 0. So it's not able to achieve that, and we see an entire row of zeros. So that's an indication that it is having multiple solutions and it cannot give us a unique solution. Let's do the same thing for the third case, which is for no solution, A3 and B3. So that's a case where we had no solutions. That's the data for no solutions, and see what we get. Again, you see here in the third row we have an impossible situation. 0x plus 0y plus 0z equals 1. That's not possible. How can you add three zeros and get a 1? So that's an impossible situation. And again, you see that in the reduced row echelon form, you do not have 1 on the diagonal. So this element should have been 1. We have not able to achieve that 1, and these should have been 0, this number and this number, but they are not 0. So because the system of equations has no solutions, uh, the process will not produce that the reduced row echelon form. Okay, so that indicates that uh, the system has no solution because we have an impossible situation in the third row here. Okay, and with that I will conclude this. So obviously this is just a very basic introduction to MATLAB. MATLAB has much more capabilities than what you've seen today. Okay, but for a start, this is some basic introduction to MATLAB related to this course. And I'll just like to show you one more command, if I still have it in my history. Okay, all right. So those were the equations that we had. That's for A, B, I think. So that was x minus y plus 3z equals 5, and so on, right? So that's x minus y plus 3z equals 5, 4x plus 2y minus z equals 0, and x plus 3y plus z equals 5, right? So we use the MATLAB's built-in command called solve to solve these equations and get the answers the solution for x, the solution for y, the solution for z, which I have named as sx, xy, sz, and we get the answer as 0, 1, and 2, which is exactly the same answer that we did. Okay, so MATLAB also has a built-in command to solve the equations, but again, when you type this command, what is happening in the background, that is one of that could be one of the methods that you have been studying in this course. Okay, so I've just given you a brief introduction to MATLAB, and I suggest that you install MATLAB on your PC and practice doing these things and work out for yourself. And the best way to learn a programming language is only by practice. Okay, I'll stop here and we'll continue in the next lecture.